Okay. So you can see I also did some annotation here. With thermal expansion, we have both a linear expansion and volumetric expansion. The linear expansion has the equation change in length is equal to the initial length times some coefficient of thermal expansion that depends on the material multiplied by the change in temperature. So since that's a change in temperature, you could use Celsius or Kelvin. It might give you units of 1 over kelvins. You can still use Celsius degrees because it's a change, and a change in Celsius is the same exact value as the change in kelvins. So that's our equation for linear expansion. Then we had volumetric expansion that was almost exactly the same. Change in volume is equal to the initial volume, beta delta T, where beta is the coefficient of volumetric expansion. And for almost every material, beta is almost exactly 3 times alpha. And that just comes from a little geometry calculation. So you have change in volume. Now I had some demonstrations. Remember I had like the ring and the circle, sphere. I put the sphere through the ring and then I heated up the sphere. It didn't fit through. How did I make the hole in the ring bigger? Heating it up. So when you heat something up, not only does it expand, holes in it will expand using the same equations. You just treat those holes as if they're made of the material, and you can calculate how much a hole expands. Now, ideal gas. What is ideal about an ideal gas? There are 2 properties. Okay? They don't stick. When they collide, they have perfectly elastic collisions, which, as you have in the last test, means that they have no change in kinetic energy when they collide. So they don't stick at all. And with that, they don't interact unless they touch. So if 2 molecules come right next to each other and don't touch, there is no interaction at all. That's ideal. Not real, ideal. The other one is the one that's a little harder to think about. And that is that they have an infinitesimal or no volume. In reality, of course, they have volume. But if you have a gas that's not very dense, then the space between molecules is so much larger than the size of the molecules that we can treat them as having roughly no volume. And if the temperature is high enough that they're not close to condensing, then we can treat them as, because the energy they lose in a collision is small compared to the energy they have, we can treat them as having the perfectly elastic collisions and not interacting unless they hit. So that's how a real gas is treated as ideal. If it's well above its condensation temperature. What's the condensation temperature for water? 100 degrees Celsius. Below 100 degrees Celsius, it's going to be liquid water. Above 100 degrees Celsius, it's going to be steam. For water vapor, steam, to behave as an ideal gas, it's going to have to be well above 100 degrees Celsius. So if you have water vapor at 150 degrees Celsius, you can't treat it like an ideal gas. But on the other hand, if you have water vapor at 500 degrees Celsius, yeah, knock yourself out. That's well away from that point of liquefaction from the condensation temperature. Now, we had a lot of physicists, and the laws are named after specific ones, but you know they kind of work together on many of these guys that studied what happens with ideal gases. And so we have Charles, I think it's Jacques Charles, who studied what happens to an ideal gas if you keep the pressure and the number of molecules constant. So you keep the pressure the same, but you change the volume. What happens to the temperature? And what he found was that volume was proportional to temperature if you're holding pressure and the number of molecules constant. And then Boyle said, well, what happens if we keep the volume constant and we let the temperature constant, we let the pressure and the volume change? And so what he found there was pressure is inversely proportional to volume. And then Gay-Lussac said, well, what happens if we hold the volume constant and the number of molecules? Yes, inversely. Thank you. I hate making mistakes, but I love it when it's corrected before we move on. Okay, so Gay-Lussac said, what happens if we keep the volume the same? And he found that pressure was proportional to temperature. Avogadro said, what happens if we allow the number of molecules to change? And he found that volume is proportional to the number of molecules. And I really don't care that you know which one is which, because if you combine the information from all four of those laws together, you get one equation of state. That one equation of state we call the ideal gas law, which says pressure times volume is equal to the number of molecules times a constant, Boltzmann's constant, multiplied by the temperature. And a lot of you have learned that relationship. What's the difference in the two? Lowercase n is defined as the number of molecules divided by Avogadro's number. And so lowercase n, the number of moles, is a number that tells you how many molecules are present, but it just doesn't have units of molecules, it has units of moles. And so R and K are similarly related. If we look at these and set them equal to each other, we see that the constant R is just equal to K times Avogadro's number. And so the two equations are exactly identical in meaning. It's just using a different set, well, a different measurement of the number of molecules present. So I am reasonably confident that everybody has worked, well, everyone except for perhaps Eric and Peter, have worked a lot with this equation. It's pretty simple. It applies to anything that's behaving as an ideal gas. It doesn't matter if it's monatomic or diatomic or triatomic. It's still going to be true if it's behaving ideally. If it's not ideal, if it is sticky, that is close to its point of liquefaction, or if it's high density, then you have to use something else like the van der Waals equation that treats a more realistic model of atoms. Kinetic theory of gases. I spent at least half of the lecture just going over the kinetic theory of gases, going over problems or a problem that, or a derivation, so you can see that temperature indeed is a measurement proportional to the average kinetic energy. Now, kinetic energy is 1/2 mv squared, so that means temperature is proportional to the average of the squared speed. Now, I'm going to actually do a problem here that deals with, well, that comes from the supplemental homework site that has the wrong words because they exist. And I want to make sure I point out to people so they understand those wrong words and what's wrong and how to do it. But you should be able to deal with that RMS speed and relate the RMS speed to the behavior of the gases. And I will give you the equations that relate the RMS speed, the average speed, the most probable speed, and the temperature. Maxwell-Boltzmann distribution is the distribution of speeds you have in an ideal gas. So in this room, we have a lot of ideal gas. We have nitrogen and oxygen. Both have condensation temperatures that are far, far below room temperature. So they're behaving as ideal gases. And since they're behaving as ideal gases, they're going to have a distribution. Some molecules have virtually zero speed. Very unlikely. Some have the RMS speed. Some are much higher than the RMS speed. And the Maxwell-Boltzmann distribution is that graph that shows you the probability of different speeds. So it has speed on this axis, and it has the probability on this axis. And there's the title. Humidity is the ratio of how much moisture the air can hold to how much moisture, well, I said it the wrong way. The ratio of how much moisture is in the air to how much moisture the air can hold. If you have 100% humidity, then the air has, that's relative humidity, I should be clear, then the air has as much moisture as it can hold. Humidity is technically how much moisture is in the air. Relative humidity is the one we always talk about. It's the ratio of how much is in the air to how much it can hold. If it's 100%, the air is saturated. It can't hold any more liquid. If you try to put more liquid in it, it's going to condense and form droplets. When you look at a cloud and you see that fluffy white cloud, you're seeing light scattering off of water droplets that formed in that cloud because it has 100% humidity. Evaporation is going from the liquid state to the gas state, and I actually have a problem with that, so I'm going to go past. Boiling is you get the temperature high enough that when you put energy, you stay at a constant temperature and it just goes, it elevates the energy to go from liquid state to gas state while keeping the temperature constant. Boiling occurs when the partial pressure of the gas is equal to atmospheric pressure. Chapter 14, heat and heat transfer methods. Make sure you can distinguish between heat, temperature, and internal energy. What are the units of heat? Joules or non-SI unit that we use a lot? Calories. Somebody said kcal. Sure, that's still calories. That's kilocalories. I'm happy. So those are units of energy. So heat is energy. Well, what's the difference between internal energy and heat? That's right. Internal energy is stored energy, or it's the combined energy of what's in the material, and heat is simply a transfer. Work is our other transfer that we've already learned about before. So what is temperature then? We've talked about it, but just now distinguishing. What are the units of temperature? Degrees Fahrenheit, degrees Celsius, or Kelvin. Notice there's no degrees with Kelvin. And it's a measurement that's telling us about the average kinetic energy. It's not the average kinetic energy, but we can calculate the average kinetic energy based on it and knowing the material. Joule equivalent of heat is just a calculation that was done to show how much work produces how much heat in calories, so that we know that 1 calorie is equal to 4.186 joules. So the joule equivalent of heat, it's just a conversion factor really, but it's important in physics, and we talk about it because originally people didn't realize that heat was just a transfer of energy. And so the experiment measuring how much work produced a calorie was important to show, yes, it's just a transfer of energy process. Work's a transfer, heat's a transfer. Then we get calorimetry. Calorimetry, you're going to have a problem in calorimetry between 16 and 20. That problem will give you 2 or 3 objects that you put together and you find the final temperature. You might have one was ice, and you find if it's 0 degrees, how much ice melted. Right? You're going to have a problem that does that. So you need to understand the basics of calorimetry, and the basics of calorimetry are dealing with heat transfer. In a calorimetry problem, you isolate your system so heat can only transfer between things inside the system. And then you just calculate the heat for each item, and the total heat is 0 if you can't transfer out, and you add them up. And so we'll go through a problem with that. Well, I'll actually show you one at very least. And remember, you have the equations Q equals mc delta T if you're changing temperature. If it's changing phase, you have Q is equal to mass times the latent heat. The latent heat is how much energy per mass is required to change phase. So you have latent heat of fusion if you're dealing with going from solid to liquid or liquid to solid, and latent heat of vaporization if you're going from liquid to gas or gas to liquid. Now, phase diagrams, I put a picture here. This picture just came from Wikipedia, source, Wikipedia. This is showing what a phase diagram looks like, has important points. The triple point is one, pressure and temperature, where you have all 3 of our common states. You have liquid, solid, and vapor, all coexisting. That's what we use. We use the triple point temperature of water now as a calibration point for the Celsius scale. That's 0.01 Celsius. So it's no longer a centigrade scale, it's a 99.99 degree scale. The critical point is the highest temperature or pressure where you can distinguish between a liquid and a gas. if you're above the critical temperature or above the critical pressure, you can't distinguish between a liquid and a gas. And then you have the phase lines. Notice this green one is for water. The green dashed one, this one here is typical. That's for typical material. So let's look at water real quickly. Again, from Wikipedia, here's a phase diagram for water. Does that look like what I showed you in class? The answer is no. No, it does not. What I showed you in class did not go up to gigapascals, right? It didn't have those huge pressures. And what you note here is the vapor, okay, nothing interesting about the vapor. This line that looked like it sloped backward when you zoom in, you can't tell it sloped backward here very much. It is a little bit. But you see it does something really curious. Come on, zoom in. Really curious up here. And then it becomes normal when you get to a pressure above 212.9 megapascals. It's good to know water becomes normal. But then there is the thing that's probably most startling. There are on this diagram designations for not all of the phases of ice, but for somewhere around, I think, 14 phases of ice. There's the cubic ice, the hexagonal ice, and then there's ice 2, 3, where's 4? I swear I saw 4. I don't see it now. 5, 6, 7, 8, 9, 10, 11 orthorhombic and 11 hexagonal, and then 15. A lot of different phases of ice. Did you know that there's different phases of ice that are all solid? Most people would say no. They just thought ice was ice. It always had the same structure. And so here's a table, the reference is down here at the bottom, for all of the different phases of ice, if you want to know. Lots of different phases of ice. And this article here is really interesting. I'm not going to go to it now, but it talks about how snow... Okay, I'll go to it. Can't help myself. Maybe I'll go to it. Maybe it won't open. There, okay. This is an article that talks about how snowflakes are formed and the history of our understanding. And what I like best is this diagram made by Nakaya. Okay, I can't write on this. I forgot. That shows you the temperature and water vapor density for different types of snowflakes. So you see the kind that we like here, the one that's marked the dendrite, occurs between about -10 and -22 degrees Celsius when you have a very high water vapor density. And you get different styles depending on the temperature. Is that cool or what? Okay, it's not going to be on the test, so let's get back to what's on the test, but I just wanted to make sure, we got something cool and interesting there. So moving on, mechanisms of heat. We had 3 mechanisms of heat. Conduction, direct contact. Convection, you have an intermediary like air that takes heat from this hot thing and transported it over here, this thing. And then we have radiation, which is electromagnetic waves. And we had equations associated with 2 of these. For conduction, the power is the rate of heating. So power is, change color here. Power is Q over delta T, the heat divided by time, is K. This K is not the Boltzmann constant. It is a thermal conductivity constant. You have to be real aware, especially of letters like K. It's used to mean constant. And it can be lots of different constants. You have to pay attention to the context. So it's going to be for any individual material multiplied by the cross-sectional area of that material. So a big pipe has a larger A, a smaller A, divided by the length, and then times the temperature difference. So if you have a bigger temperature difference between 2 things, the heat's going to flow faster. If it has to travel a larger distance, it's going to flow slower. And if you have a bigger area, it's going to go faster again. For radiation, we have this much more complicated equation. And remember, epsilon, yes, epsilon, that is right, is the emissivity. It's telling us how well something absorbs and emits radiation. If it's black, it's going to have epsilon very close to 1 because that's the perfect color for absorbing or emitting radiation. Then you have sigma there, that's just a constant, the Stefan-Boltzmann constant. A is the surface area. So when we looked at this equation, A was the cross-sectional area, the area the heat's going through, whereas in the radiation, A is the entire surface area. Different meaning for the same word area. And then it's the difference of temperatures to the fourth. Remember, the difference in temperatures to the fourth is a very different value than the fourth power of the difference in temperatures. You have to put temperature of the object to the fourth minus temperature of the environment to the fourth. And that's going to be the rate that power is, the net rate that power is emitted from an object. All right, the last chapter, thermodynamics. We've learned about isothermal processes, isochoric, isobaric, adiabatic. Another name for adiabatic is isentropic. There's also another name for isochoric, and that is isovolumetric. So make sure you understand those processes. I gave you a homework problem that asked you to relate the change in internal energy, the work, and the heat for all of these. Now, with that homework problem, I was going through with a few students this morning, so you can see the first parts A and B done if you go to the right place on OneNote. You have to be aware that it says specifically it's talking about the work done on the system. In class, we've always talked about the work done by the system. Well, if the system is doing work done by the system is positive, then energy is going out. If work is done on the system, energy is coming in. So you have to pay attention to those little words. And so I was telling the students this morning, the key is if you have force in the same direction as motion, then you're doing work. And so if a gas expands, then the force it's going to put on the environment is outward, and it's going to move outward, so it's doing positive work if it expands. You can use that to make sure you get your sign straight. Thermodynamic work is equal to pressure times change in volume. And remember, that's pressure times change in volume, not change in pressure times volume. And so for people who are in the general physics class, Physics 151, if you have a changing pressure, the only way you can find the work is by taking the area under the curve. If it's a straight line graph, then you take your pressure times volume or by volume graph, and you just find the area underneath that. If you have a cycle, you take the area enclosed for the net work. If you're in the calculus class, you can actually integrate it. Reversible processes are processes that have no change in entropy. Don't worry about the reversible process, actually. I should have crossed that out. Second law of thermodynamics, we learned from the get-go, energy spontaneously flows from the higher temperature to the lower temperature. What do we call that flow of energy? Heat. So heat flows from higher temperature to lower temperature. There is the second statement I have here, the entropy statement, the entropy of the universe never decreases. We didn't talk much about entropy at all, so I'm not going to ask you about this statement either because we didn't talk about it enough. Heat engines, last thing we talked about. Heat engines, what's the purpose of a heat engine? It is to do work from, well, it is kinetic energy, but it's microscopic. It's thermal energy. We're going to take thermal energy, transport heat, that's the transport of thermal energy, and convert that into work. That's the purpose of a heat engine. A heat engine always is going to have waste heat. It's going to exhaust heat at a lower temperature. And so you never have a perfectly efficient heat engine. The efficiency is the work that's done by the engine divided by the heat you put in at high temperature. The Carnot Cycle, adiabatic expansion followed by isothermal expansion followed by adiabatic expansion, then isothermal contraction followed by adiabatic contraction. That's the Carnot cycle, and it's been shown mathematically that it gives you the best efficiency possible for your temperature of your hot and temperature of your cold environments. So the Carnot cycle is useful because the Carnot efficiency is the best possible efficiency, and it's your temperature cold over temperature hot minus temperature cold is what it turns out to be. Okay, that's the end of what we're going to cover. I have a few problems here. This one here is from the supplemental homework problems. It says that near the sun's surface, the temperature is 1.5 times 10 to the 7th. K, what's K mean? Kelvin's K. For the average velocity RMS. Everybody see a problem? Average velocity and RMS velocity are two different things with different equations. And so this here, the person who wrote it was not thinking clearly. And we have multiple versions of this question. On the test, if I were to take something like this, I wouldn't put in the wrong words. So for the velocity VRMS to equal the escape velocity of the sun, what is that velocity? Well, you just say, VRMS is equal to square root of that's an R. What's the difference in those two equations? This one that has the constant K is using the atomic mass, the mass for a single atom, and the one that's using R is using the molar mass, the mass for a mole of the gas. Once again, there are some problems that says it has an atomic mass of 44.0 grams per mole. That's not the atomic mass, is it? That's the molar mass. So there are some problems with wrong words. I'm glad we're not using that for homework for credit, because with those wrong words, who can expect a student to decipher it exactly? So you would take this and you would just simply calculate the RMS velocity, putting in the temperature that was given in units of kelvins because it's not a change in temperature, and you get your answer. Did somebody have a question on this? Okay, calorimetry problem. This is a standard calorimetry type problem. You have a liquid, in this case coffee, that says treat it like water. And you put it in your glass cup, and you want it to cool from 95 degrees Celsius to 45 degrees Celsius. And then ask how much evaporation you're going to have, assuming that it requires this many kilojoules per kilogram to evaporate. Well, to do this, it's a calorimetry problem. I identify it's a calorimetry problem because I have a lot of experience. Because I know that I'm putting these together and heat's going to transfer from one thing to another. And so I'm going to take, for any calorimetry problem, I'm going to start with the sum of the heats is equal to 0. And then I'm going to, the heat for the coffee, it's changing temperature, not changing phase. So that's going to be MC delta T. Delta T is going to be temperature final minus temperature initial. Since it's going down, delta T is a negative value, so that Q is going to turn out to be negative. I strongly recommend don't throw an artificial negative sign in there. Just keep your equations Q is equal to MC delta T, and if the delta T is negative, the Q is negative. Then you also have the Q for evaporation, which is going to be mass times the latent heat. Now, if it's evaporating, you're putting heat into it, right? And so heat is going out of the coffee and into the steam. And you're like, which direction is that going to be? Aren't you? No? Yes. Well, that's going to be with the positive side in this case. And you're also going to have Q for the glass. Mass of the glass, C of the glass, delta T for the glass, which is the same as delta T for the coffee. And then you do the sum of those heats is 0, and you solve for M. Now, there's one more thing that it says the average heat of vaporization is this. There are some things that can be confusing, like if I am at body temperature and I have evaporation occurring from my water on my skin, there is not heating the water up to the boiling temperature of water and then boiling. It's a different heat of vaporization at my body temperature than it is at boiling temperature. This here is, I'm pretty certain, the heat of vaporization at the temperature of the water, and we just don't worry about any change there. I'm going to go through this, and then I'm going to stop. I should have stopped 3 minutes ago. Give an example of convection found in nature. I'm not going to have you just circle one here. I'm going to ask you, what is the first one? Heat transfer through a metallic rod. Which kind of heating is that? That's conduction, because it's going through a physical object. Heat transfer from the sun to the earth. What's that? Okay, we're good at this. I'll put something that quizzes you on this on the test. Heat transfer through ocean currents. Convection. Hey, let's put a circle around that one. Heat emitted by a light bulb into its environment. Okay, we got it.